Hello everyone. In this video, in this video, I will discuss about inverse of a matrix and a method for finding inverse of a matrix. Let us start with the definition of invertible matrices. If A is a square matrix of order M and if there exists another square matrix B of the same order M such that AB equal to BA equal to identity, then B is called the inverse of A. That means if A is a square matrix of order M and if there exists another square matrix B of the same order M such that AB and BA are identities, then B is called the inverse matrix of A and it is denoted by A inverse. In that case, we say that A is invertible. For example, if A is equals to 2, 3, 3, 5 and B is equals to 5, minus 3 and minus 3, 2. These are the two matrices of order 2 by 2, that is both are square matrices of order 2. Now it can easily be verified that both product AB and BA are identities. Both product AB and BA are identities. So since both AB and BA are identities, we can say that B is the inverse of A. That is, it is written as A inverse equal to B. If A is inverse of B, then we can write B inverse equal to A. A is inverse of B, that is B. If B is inverse of A, then it is true that A is inverse of B also. That is, if A inverse equal to B, that implies that B inverse equal to A. There are some points to be noted. First one, a rectangular matrix does not possess inverse matrix. Since for products BA and AB to be defined and to be equal, it is necessary that matrices A and B should be square matrices of the same order. Because of this reason, a rectangular matrix does not possess inverse matrix. Only square matrices have inverse. For example, if you consider a 2 by 3 matrix and B a 3 by 2 matrix, then AB and BA will be of different order. They won't be of same order. Here AB is of order 2 by 2 and BA is of order 3 by 3. Naturally, a question arises, does every square matrix possess inverse? The answer to that is no. Every square matrix need not possess an inverse. There is a condition for existence of inverse of a square matrix which will be discussed in the next chapter. Second point, if B is the inverse of A, then A is also the inverse of B. That is already discussed. If A inverse equal to B, then B inverse equal to A. Now next two simple theorems. First one, inverse of a square matrix, if it exists, is unique. That means if a square matrix has an inverse, then the inverse will be unique. So it is a very simple proof. Suppose A is a square matrix of order M. So we are assuming that B and C are two inverses of A. So we want to show that the inverse is unique. That means we have to show that B equal to C. Now since B is the inverse of A, AB and BA are both identities. This is by using the definition of inverse of a matrix. Since C is also the inverse of A, AC equals to CA equal to identity. We have to prove that B equal to C. Now B can be written as B into identity. So that is identity matrix of the same order M. Here we are considering A, B, C are matrices of order M, that is square matrices of order M. So B can be written as BI. Since I equal to AC, from the second equation we can write it is as B into AC. This can be written as BA into C. Again from equation 1, BA equal to I. So using that BA we can write it as I. So it will become I into C. Again I into C equal to C. So we have proved that B equal to C. So we assumed that B and C are two inverses of A, and we proved that B equal to C. So that means that the inverse of a square matrix is unique. So no square matrix will have, if it possesses an inverse, will have more than one inverse. The inverse will be unique. Now second theorem, it's a property of invertible matrices, that is if A and B are invertible matrices of the same order, then AB inverse, that is inverse of the product AB, it is equal to B inverse into A inverse. Now again from the definition of inverse of a matrix, AB multiplied with AB inverse will give us an identity matrix, that is AB into AB inverse equal to identity matrix. Now if you multiply both sides with A inverse, multiply LHS and RHS of the first equation with A inverse. Again using the associativity of matrix multiplication, A inverse into AB can be written as A inverse A into B. So using that, this equation can be written as A inverse A into B into AB inverse. That is, this whole equation is changed into A inverse into AB equal to A inverse A into B into AB inverse. And here A inverse I becomes A inverse, since any matrix multiplied by identity will give you the same matrix. Again, a matrix multiplied by its inverse will give you an identity. So A inverse A equal to I, B then AB inverse is equal to A inverse. So now I into B, again it can be written as B. So B into AB inverse equal to A inverse. Now multiply both sides of this equation with B inverse. So it will become B inverse into B equal to AB whole inverse. So right hand side will become B inverse into A inverse. So again B inverse into B is equal to identity. So it will become I into AB inverse. So I into AB inverse, RHS will become B inverse A inverse. So I into AB inverse is nothing but AB inverse. So thus we got AB inverse equal to B inverse A inverse. Next, let us discuss a method for finding inverse of a matrix. The method is called as elementary operation of a matrix, that is finding the inverse of a matrix using elementary operation or elementary transformation. There are 6 elementary operations or transformation, 3 of which are due to rows and 3 of which are due to columns. First one is the interchange of any 2 rows or 2 columns. So that means if we interchange ith and jth rows, it is denoted by Ri interchanges with Rj, and if we interchange ith and jth column, it is denoted by Ci interchanges with Cj. For example, suppose if we interchange first and second row to the matrix A, so we will get a matrix in which, so once we apply R1 interchanges to R2, we will get a matrix in which first row in A will become second row and second row in A will become first row. That is a matrix obtained by interchanging first and second row in A. Similarly, if C1 interchanges with C2 is applied to A, the first and second column here will get interchanged. So first column here will become second column and second column here will become first column. So this is the first of the elementary transformations, that is interchanging any 2 rows or interchanging any 2 columns. Now to the second elementary transformation, that is multiplication of the elements of any row or column by a non-zero constant. So if we are multiplying ith row by k, then where k should not be 0, it is denoted by ri changes to k times ri, and similar operation for column, that is ci will change to k times ci. So for example, suppose if you apply the operation R1 changes to 2 times R1. So if 1, 2, 3 are elements of R1 here, each of these elements will get multiplied by 2. So it will become 2, 4, 6. So here you see that each once we apply R1 changes to 2R1, so each element got multiplied with 2. Similarly, if we apply C2 changes to 3C2, again the second column, all the elements of second column will get multiplied with 3. So using this, any row or column of a matrix can be multiplied by any constant. Only condition is that the constant should not be 0. So the third and final elementary operation is addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number. That is, if you want to change Ri, you can change it using this. Ri changes to k times Rj. That means multiply elements of jth row by k, then add it to the corresponding elements of ith row. Similarly, Ci changes to Ci plus k times Cj. This means that elements of jth column multiplied with k are added to ith row, and ith row is changed using this, that is Ci changes to k times Cj. For example, suppose we apply R2, second row changes to second row plus first row. So here we are using second row plus 1, the constant k is here 1 times R1. So the change we have to make to second row. So the second row here is minus 1, 3, 1. So that second row will now change to R2 plus R1, that is second row plus first row. So you have to add the corresponding elements. So minus 1 will change to minus 1 plus 1. So that means it will become 0. And 3 will change to 3 plus 2. That is second row plus first row. So it will become 5. And similarly, 1 will become 1 plus 3. That is equal to 4. In the same way, if we apply the transformation C3, that is third column changes to third column minus 3 times first column. So here the elements of third column are 3, 1, 1. So using this transformation, each element will change to C3 changes to C3 minus 3C1. So you take a particular element, that is 3 here, 3 minus 3 times first column. So it will become 3 minus 3. So that is 0. Then 1 minus 3 times minus 1. So minus 3. So that is 1 minus of minus 3. So it will become 4. Then 1 minus 3 times 4, that is 1 minus 12. So it will become minus 11. So the transformation here is C3 changes to C3 minus 3 C1. So each element of C1 is multiplied with 3. Then C3 minus 3 C1. Here also the constant should not be 0. So constant, if is 0, there is no transformation happening. That is Ri will change to Ri only if k is taken as 0. So these are the 6 transformations, that is 3 of which are due to row and 3 of which are due to columns. So the first one was interchange of 2 rows or 2 columns. Second one, multiplication of elements of any row or column by a non-zero constant. And third one, addition to the elements of any row or column corresponding elements of any other row or column multiplied by a non-zero number. So for finding the inverse of a matrix by elementary transformations or elementary operations, we'll be using only these operations. These are the standard elementary operations on a matrix. So next we'll go to what are the uses of this elementary operation or transformation. Suppose X, A and B are three matrices of the same order such that X is equals to AB, X is equals to AB. So if you want to apply a sequence of elementary operations on this equation, on this matrix equation, so this is an equation involving matrices where X, A and B are matrices of the same order. So X is equals to AB is a matrix equation. So in order to apply a sequence of elementary row operations on this matrix equation, it is needed to apply this row operation simultaneously on X, that is the left hand side matrix, and on A only, that is the leftmost matrix of the product AB on the right hand side. So to apply a sequence of row operation on a matrix equation, that is X is equals to AB, it is needed to apply only on the right hand side leftmost matrix, that is the first matrix A of the product AB on RHS. It is not needed to apply on the second matrix of the product AB on the right hand side. So similarly, in order to apply a sequence of elementary column operations on the matrix equation X equal to AB, we'll apply these operations simultaneously on X and on the second matrix B of the product AB. So to apply a sequence of column operations, it is required to be applied only on the second matrix of the product AB. So I'll explain this with a simple example. What does this mean to an equation involving matrices? So you consider a system of equations in two variables. System of equations in two variables, that is 3x plus 4y equal to 12 and 2x plus 3y equal to 4. So this system of equations, that is 3x plus 4y equal to 12 and 2x plus 3y equal to 4, can be written using matrices. So this can be written as 3, 4, 2, 3, and that is the coefficient matrix 3, 4, 2, 3. Then x comma y, that is the matrices of the variables, equal to 12 and 4, that is the right hand side constants. So now if you multiply this, you will be getting the same equation 3x plus 4y equal to 12, then 2x plus 3y equal to 4. So if we apply R1 changes to 2 times R1 to the first equation, that is this matrix equation, you have to note that this is a row operation, so it needed to be applied only on the first matrix of the product AB. So that means R1 interchanges to 2R1, we will get 6, 8, that is only first matrix of the product. So 3 and 4 will get multiplied with 2, and second row will remain as it is. Second matrix, there won't be any change, that is x comma y, and it's equal to 24, 4, that is the same simultaneous, only the operation is conducted on the single matrix on left side or right side. So what we have done here, we have applied the row operation simultaneously on the first matrix of the product and on the right hand side. So here we now this, after transforming this, the equations which we get are like this. The first equation only will change, that will become 6x plus 8y equal to 24. There won't be any change in the second equation. So here, after applying the row transformation, we are getting an equivalent equation. So R1 changes to 2R1. This means that we are getting an equation in which the first equation is multiplied with 2. Now suppose if we apply this R1 interchanges to 2R1 to the second matrix of the product, that is, instead of changing the rows of the first matrix, if we change the rows of the second matrix, that is R1 interchanges with R1 changes to 2R1 to the second matrix, then we will be getting 3 4 2 3. Then first row of the second matrix will change, that is it will become 2x comma y. So the entire equation will change. We will not get an equivalent equation. So in order to apply a row transformation, it is needed to apply on the first matrix of the product. It has to be the first matrix of the product, and simultaneously that should be applied to the matrix on the right hand side or left hand side, which will be a single matrix. And in the same way, if we apply the column operation, that is C1 interchanges to 2C1, then it should be applied to the second matrix of the product, not on the first matrix of the product. So column operations here, C1 changes to 2C1, are to be applied simultaneously to the second matrix of the product and on the right hand side matrix. So here again, if we change C1 changes to 2C1, it should be applied to the second matrix. So here equation 1, second matrix is x and y. So it will change to 2 times C1, so it will become 2x and 2y. So right hand side matrix, only one matrix is there, that also will get multiplied with 2. So this is equivalent to multiplying both given equation with 2. So you'll get an equivalent equation where both the equations are multiplied with 2. So in a matrix equation x equals to AB, in order to apply a sequence of row transformation, it is to be applied only on x and A, the first matrix of the product, simultaneously, and in order to apply a column transformation, it should be applied to x and B simultaneously. Here I took simple example. So this result is valid for any matrix equation. Even if the matrices x, A and B are of the same order, then also this result is valid. That means if you want to apply a sequence of row operation, it needed to apply only on the first matrix of the product, and in order to apply a column transformation, it is needed to apply only on the second matrix of the product. So in order to use this for finding inverse of a matrix, so to find A inverse using elementary row operations, we have to write A equal to IA. A equal to IA. A can be written as both IA and AI. So since we are applying row operations, we have to write A equal to IA. And using the above result, we are applying a sequence of row operations. Sequence of row operations on this equation A equal to IA. That means we have to apply a sequence of row operations on A and on I, that is the first matrix of the product. So because of that reason only, we have to write A equal to IA in order to apply elementary row operation. And after applying a sequence of operation, we have to apply sequence of operations till we get I equal to BA. The row operation needed to apply only on A on the left hand side and I on the right hand side. It need not be applied on A, that is the second matrix of the product. So we got I equal to BA. So now we will use the definition of inverse. We can say that B is the inverse of A. So similarly, if we wish to find A inverse using column operation, so again using the above result, column operation needed to apply only on the second matrix of the product. So in order to apply column operation, we have to write A equal to AI. So A equal to AI and apply a sequence of column operations on A equal to AI, that is this matrix equation. So we have to apply it on A on the left hand side and on I on the right hand side till we get I on the left hand side. That means we will get an equation of the form I equal to AB. So we are changing A on the left hand side and I on the right hand side, that is second matrix of the product. This is using column operation. So you have to note that in order to apply row operations we have to write A equal to IA, and in order to apply column operations we have to write A equal to AI. Now suppose after applying one or more elementary row or column transformation A equal to IA or A equal to AI, if we obtain all zeros in one or more rows of the matrix A, then A inverse does not exist. So that means after applying a sequence of row operation, one complete row becomes 0 or what complete column becomes 0, then A inverse does not exist. So now let us see some examples. So in all these examples, I have used row transformation only. That means I have started with A equal to IA and applied a sequence of row transformation till I got I equal to BA. So if you want to apply column transformation, you have to start with A equal to AI. So let us start with a 2 by 2 matrix, that is square matrix of order 2. So first matrix is 1 minus 1 2 comma 3. So I assume that A equals to 1 minus 1 2 3. So write A equal to IA. Because I am using row transformation, I wrote A equal to IA. It can be either A equal to IA or A equal to IAI depending on whether you are using row transformation or column transformation. Because I am using row transformation, I started with A equal to IA. So that means the equation is written like this: 1 minus 1 2 3. Right hand side is, first one is identity of the same order. Since it's a 2 by 2, we will take identity of 2 by 2. And right handmost A, since we are not applying any row transformation to the second matrix of the product, it is written as A only. No need to write it as a matrix because we are not changing any changes to the second matrix of the product. So what is our aim is to get identity on the left hand side. We have to select row transformation in such a way that we have to get identity on the left hand side. That means we have to get 1 0 0 1 on the left hand side. Changes are to be made to the left hand side matrix so that we get identity matrix. The same changes needed to apply on the identity matrix already there on the right hand side. So first element is 1 already is there. So first element is 1, then I should get 0 here, 1 0. Instead of 2 I should get 0. That is a part of the identity matrix. So we are making it identity matrix. That means we should get 1 0 0 1. So first I started with 1. 1 is already, that is 1, so no need to change the first element. Then A to 1, so it should be 0. So the transformation I am using here is R2 changes to R2 minus 2R1. So R2, the second row will change, R2 will change to R2 minus 2 times R1. Now that means first row no change. So second row will be changed, 2 minus 2 times first row. So 2 minus 2 I'll get 0. Then 3 minus of minus 2, it will become 5. The similar changes to be made on the right hand side matrix. So that is 0 minus 2 times 1, so it will become minus 2. 1 minus 2 times 0, so it will come as 1 on. So after applying R2 changes to R2 minus 2R1, we got 1 0 here. Now we want 0 1 here. then only it will be become an identity matrix. So now for that we need 1 here. So what transformation I used here? R2 changes to 1 by 5 R2, directly multiplying second row with 1 by 5, so that it will become 1 0 minus 1 1, because I multiplied with 1 by 5. So that is using the second transformation, second of the elementary transformation, multiply with a non-zero constant. So R2 changes to 1 by 5 R2. So that means it will become 1 0 0 1. Similarly, the second row here also needed to be multiplied with 1 by 5, so it will become minus 2 by 5 and 1 by 5. So now we got 1 0 0 1 here also. Now we have to change only this element so that we will get 0 here. So that means we got identity matrix. So in order to get 0 here, I used the transformation R1 changes to R1 plus R2. That means first row is changed to R1 plus R2, first row plus second row. So it will become 1 0 0 1, the left hand side. A similar transformation to be used on the right hand side also. R1 changes to R1 plus R2, that is 1 minus 2 by 5, 0 plus 1 by 5. So now finally we got identity on the left hand side. Once we get identity on the left hand side, the problem is over. And whatever matrix you get on the right hand side, this is the inverse matrix. So here left hand side we got identity, that is 1 0 0 1. So the right hand side matrix will be the inverse. So A inverse is equals to 3 by 5, 1 by 5, minus 2 by 5, 1 by 5. So some points to be noted here. If you write A equal to IA, you have to use row transformation. You cannot write A equal to IA and use column transformation. And similarly, once you write A equal to IA, you are starting with row transformation. You cannot change to column transformation in between. Once you start with row transformation, you have to use row transformation throughout. And one more thing, these transformations are not unique. There are different transformations. These are a set of transformation which will give you identity. There are different types of transformation that can also be used. But all these transformation will give you the unique final answer. The final answer will not be different. And you have to use the elementary transformations in each of the steps. Now we will go to the second example. So here again 2 by 2 matrix 2 1 1 1. So I am using row transformation. So A equal to IA. So I started with A equal to I. You can follow a simple algorithm. That means we want to get identity matrix on the left hand side, that is this should be converted to identity matrix. So we have to get 1 0 0. So we have to get identity on the left hand side. That means we should get 1 0 0 1 on the left hand side. So start with the first element, that is A11. If it is already 1, move to the second, that is A21, in the element in that same column. So the algorithm you can follow is start with the first element. If it is 1, move to the element in that column, make that 0. Then again move to the A22, that is the next diagonal element, make that 1. Then again move to the column to make it 0. So here 2 comma 1, so it is not 1. So the simple transformation you can use is divide the complete row with whatever number is coming as the first element. So here it is 2 comma 1. So if I divide this with R1 changes to 1 by 2 R1, then I will get 1 by 2 here. And I used another transformation just to show that there are different transformations. So that is by interchanging rows and interchanging first and second row. So if I apply R1 interchanges with R2, then also I will get 1. So this is actually here in this particular problem I am getting this because 1 is there in the A21 position. I will not get it if 1 is not there in the A21 position. So in that case you can follow the simple algorithm. Just divide the first row with that what particular element is there in the A11 position. So here I used R1 interchanges with R2. I got 1 1 2 1, then 0 1 1 0. That is interchanging the rows of identity matrix also. Now to get identity, here it should be 0. That is whatever element is there, 2 is here. So you just use R2 changes to R2 minus how many times whatever number is there that times R1. So here 2 is there, so R2 changes to R2 minus 2R1 because 2 is here. If 3 is there, then you have to use R2 changes to R2 minus 3 times R1. So we got 1 1 0 minus 1. So now we have to take care of this column only. So again let's start with the diagonal element, that is we will make it 1 first. So R2 changes to minus R2, that means multiply the second row with minus 1 because here minus 1 is there. So if suppose 2 is there, so you have to multiply with 1 by 2. 5 is there, like in the previous problem we multiplied with 1 by 5. So after applying R2 changes to minus R2, we'll get 1 0 0 1. And now we need to change only this element, so that we can do it by R1 changes to R1 minus R2 because 1 is here. Suppose 2 or 3 is there, then R1 changes to R1 minus 2R2 or 3R2 depending on what number is here. So if I applying R1 changes to R1 minus R2, we get 1 0 0 1. So all these transformation which we are doing on the left hand side needed to be performed on the right hand side identity matrix, and finally whatever matrix comes on the right hand side, that will be the inverse. Okay, once you get identity on the left hand side, whatever matrix comes on the right hand side with A, that will be the answer to the problem. A inverse is equals to 1 minus 1 minus 1 2. Now we come to the third example, 2 1 4 2. So again I am using row transformation, write A equal to IA. So 2 1 4 2. So the first element is 2 here. First element is 2. So that means I should get 1 here. So in order to get 1, I will divide the first row with 2 or multiply it with 1 by 2. So R1 changes to 1 by 2 R1. So now I got 1 here, 1 1 by 2, then 4 and 2. Now here 4 is there, so I should get 0. So in order to get 0, second row I will change it to second row minus 4 times first row because 4 is here. So R2 changes to R2 minus 4 R1. So it will become 4 minus 4. So it will become 0. Now you see that when we apply this transformation, second row completely becomes 0. Second row completely becomes 0. Now if during the process of applying row transformation or column transformation, if you get any row or column completely as 0, then inverse does not exist. Inverse does not exist. Now from this we will not get identity on the left hand side because it is 0 0 is there in one complete row. So since second row of left hand side are all zeros, the inverse does not exist. So once you get zeros in any row or column completely, then you can stop there and the inverse of such matrix does not exist. So now we will move to a 3 by 3 matrix, finding the inverse of this matrix using elementary transformation. Again I am using row transformation. So I am starting with A equal to IA. So the aim is to get identity on the left hand side. So our aim is to get identity on the left hand side, that is 1 0 0 0 1 0 0 0 1. So again start with the first element. So first element is 2. So the first transformation can be used as R1 changes to 1 by 2 R1, so that we'll get 1 here. So R1 changes to 1 by 2 R1. So that means the elements will change 1 minus 3 by 2, 3 by 2. Then second and third row will remain as it is. The same transformation needed to apply on the right hand side also. Again, I am repeating, these transformations are not unique. These are a set of transformations. There are other transformations also. So after getting 1 here, now as part of the identity, you should get 0 here, 0, 0. Both should be converted to 0. So for that, we can use the first row. So the transformation here is R2 changes to R2 minus 2R1 and R3 changes to R3 minus 3R1. Note that here we can use two transformations at a time. So in the previous problem, that is 2 by 2 problems, we used to do only one transformation at a time. But in the case of 3 by 3 matrix, you can use two transformation at a time. Only thing to be noted is that we are changing R2 here. So R2 is changed here. So we are changing R2. So for changing the other row, you cannot use R2. So this should be independent of R2. Then only you can use two transformation at a time. So again, simple idea, you can, if whatever the number here 2 and 3 are there, so second row you can change, second row changes to second row minus 2 times first row, third row changes to third row minus 3 times first row, because 2 and 3 are there. Depending on the number, it will change. So R2 changes to R2 minus 2R1 and R3 changes to R3 minus 3R1. So now we got 1, 0, 0 here. Then similar changes will occur on the other elements also. That is minus whatever changes we are making. First row here no change. Second and third row it will change accordingly. Now again we come to the A22 element, that is the diagonal element. After making it 1, 0, 0, now you will come to the diagonal element here. We have to convert it into 1. So it's a very simple idea. You just multiply with whatever number that is reciprocal of that. So if 5 is there, you multiply with 1 by 5. So R2 changes to 1 by 5 R2. So 1, 0, 0, then minus 3 by 2, 1, 5 by 2. So we got 1 here. That is just by multiplying second row with 1 by 5. Now our aim is to get 0 here. These two positions, 0 we should get. That is the part of the identity matrix 1, 0, 0, 0, 1, 0. So for that, again you see the numbers here. It is minus 3 by 2. So if I apply, R1 changes to R1 plus 3 by 2 R2. That is because minus 3 by 2 is there. I took plus 3 by 2 R2. So then I will get 0 here. Similarly, 5 by 2 is there. So if we apply, R3 changes to R3 minus 5 by 2 R2. So R1 changes to R1 plus 3 by 2 R2, R3 changes to R3 minus 5 by 2 R2. So you'll get 0, 0 here. This, whatever changes you are making, that should be made on the right hand side matrix also. So we got 1, 0, 0, 0, 1, 0. Now we need to get 0, 0, 1. So again we'll start with 1. So we'll make this 1. So it is minus 5 by 2 is there, multiply with the reciprocal. So R3 changes to minus 2 by 5 R3. So we got 0, 0, 1. Okay, 0, 0, 1 here. Now here we have to change, we have to get 0, 0 on the column. So but this is already 0 is there. So we need to change only this. So again you see the number here 3 by 2. So 3 by 2, so that means you have to use R1 changes to R1 minus 3 by 2 R3. So once we use R1 changes to R1 minus 3 by 2 R3, you'll get identity, complete identity on the left hand side, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. So whatever changes you are making here, you should make it on the right hand side matrix also. So that means we got I equal to BA. So the problem is over. So whatever we got on the right hand side, that is the inverse of the matrix A. So one more example. So here 2, 0, minus 1, 5, 1, 0, 0, 1, 3. So 2, 0, minus 1. So I wrote A equal to IA. 2, 0, minus 1, 5, 1, 0. So again, since 2 is there, I have to make R1 changes to 1 by 2 R1. So that I will get 1 here, 1, 0, 0. So that's we got 1 here, 0 is already there. So now we need to change 5. So in order to change 5, it should be converted to 0. So that means can use R2 changes to R2 minus 5 R1. So once we use R2 changes to R2 minus 5 R1, we will get 100 here. Okay. So as a part of this we are getting 0 1 1. 0 1 1, that means the diagonal element is already 1 and the first element is already 0. This is by using the other transformation. So we need not change it separately. We already got a part of the identity. So 0 and 1 we already got it here. So we need to change only this 1. So this is in third row and the number is 1. So the changes R3 changes to R3 minus R2. So now we got 1 0 0 0 1 0 here, 1 0 0 and 0 1 0. So now we need to look in the third column, that is you see the 1 by 2 here. So that means you have to multiply it with 2. So R3 changes to R3 to R3. So you get 1 here. So finally we need to get 0 0 here. So you see the numbers are minus half and 5 by 2. So R1 changes to R1 plus half R3, R2 changes to R2 minus 5 by 2 R3. So two transformation at a time, and make sure that the second transformation does not involve the row which we are changing here. So this should not involve R1. So that's why I used R2 changes to R2 minus 5 by 2 R3. So after applying these two transformation, we will get identity on the left hand side. So we got identity. All these transformation applied on the right hand side matrix also. Then we will get this matrix 3 minus 1, 1 minus 15, 6 minus 5, 5 minus 2 and 2. So that is the A inverse of A. So A inverse equals to 3 minus 1, 1 minus 15, 6 minus 5, 5 minus 2 and 2. So you can verify the answer just by multiplying with the question whatever matrix is there. Since this is the inverse, the product of A and A inverse should always give you the identity matrix. Again I am repeating, these are not the unique transformation. There are other transformations which can also be used. Okay, that's it for this lesson. Thank you for listening.